Let's see. So, Chapter 2 deals with energy and capacitance. More particularly, we're going to be dealing with potential. But potential is really just a measure of energy. So, you could replace this and just say potential. So, we're dealing with these big ideas. We had force, and then we had field, which were a measure of force per unit charge. And now we're going to be dealing with potential, which is a measure of energy per charge. So whenever we talk about the energy of a particular configuration of charges or of a particular charge, it's all about what is the energy per charge. So we have forces and then fields, which are forces per charge, and then we know potential, which is energy per charge. First of all, though, electric forces are conservative. Remember, when we were talking about conservative forces, we said there are basically two forces that are conservative. Gravitational forces and electric forces, and collectively those are what type of forces? Field forces. So they don't require contact. Those are really, there are some others like interatomic forces, but as far as forces that we deal with every day, electric and gravitation are the only conservative forces, are the only field forces. Conservative means it conserves what? Right. All right. So conservative forces conserve energy. And because they're conservative, they're also path independent. Hey, Hunter. We talked about this last semester, how a conservative force, like a gravitational force, I'm taking this bottle of water that somebody left in here like 2 weeks ago. If I move it, or if I go from here to here, I gain a certain amount of energy. Likewise, if I go from here to here, I gain the same amount of energy. And that's because conservative forces are path independent, right? Whereas a frictional force, if I move it from here to here, I lose a certain amount of energy because of the friction. However, if I move it from here to here, do I lose more or less or the same energy? I lose more energy because the frictional force acted over a larger distance, right? So friction is a great non-conservative force. It doesn't conserve energy, and it is path dependent. It does depend upon the path. So just sort of in words, conservative is a force that conserves energy. You can see a multiple choice answer. We've had these before. Hopefully it'll be a gimme question. A force that conserves energy, the amount of work done by the force changes the energy by the same amount. All right, so for example, if I have something in the gravitational field and I drop it, that gravitational force does a certain amount of work. Because I have a force over a displacement and it does a certain amount of work. It also changes the amount of energy by that same amount. So whatever work the gravitational force does, it changes the energy, kinetic energy at this point. We did conservation of energy last semester. That was what that was all based on. That the amount of work done by the conservative force changes the energy by the same amount. And gravity and electric forces are sort of our token conservative forces. And then non-conservative forces don't conserve energy. And friction is a good example. The work done by conservative forces is path independent. And the work done by non-conservative forces is path dependent. We've seen all this before, so hopefully this is sort of jogging your memory about this. All right, so for example, like if you have a guy going down a slide and you have a guy jumping from the same point, the gravitational force is doing the same amount of work on them, but which one has more energy when he gets to the bottom? the one following has more energy because this also has that non-conservative force of friction acting on it. So as it goes down this path, it actually loses energy. And if this guy takes a different path, say like this, then he'll lose even more energy, right? Because he's going for a longer distance, and that friction acts over a larger distance, taking away more energy. So the work done by gravity is still the same. So this is like the pencil here. If I drop a mass, like the pencil I dropped here, the gravitational force is doing a certain amount of work. And that's right here. It's equal to m times g times delta x. Right? Because the gravitational force, the force is in this direction, x is in this direction, so it's negative. And so I have this work that's being done, it's negative, and then that work is equal to that object's change in energy. The change in potential energy in particular. These are all just sort of semantics. When we get into the mechanics of it, you're not going to be dealing with too much of this. So in a similar way, since gravity and electric forces are very similar, they both sort of have the same form, then we can write the same thing about gravitational forces. That is that the change in potential energy is equal to the negative of the work when you're going between 2 points A and B. That's the same as negative force times my delta x, which is equal to negative QE. Remember, the force is QE times delta x. Right, so I have my change in energy is equal to this negative QE delta x. So we'll see how that comes up in just a bit. And this applies when the electric field is constant and unchanging, or it's constant. Let's not worry about this little aside here. It's not terribly important. All right. So let's look at this example. This is going to be a capacitor, by the way. So a capacitor are just two parallel plates. And so we'll see capacitors later in this chapter. But right now, just imagine that we have two plates. One has positive charges all along here, and then one has negative charges all along here. So we have a constant electric field between the two. We have electric field going from right or left to right, from the positive to the negative charges. And if I move a charge, a positive charge, from this direction to this direction, has the electric field done A positive or B negative work on this positive charge? So use your clickers. Has it done A positive or B negative work? Actually, let me get my clickers up. Alright, so has the electric field, right, this electric field exerts a certain force, moves this charge a certain displacement. Has that electric field done positive or negative work on this positive charge? Morning, guys. Positive or negative work? Alright, taken away in about 3 seconds. I'll stop at 33. Okay. A is the right answer. My force is in this direction, right? Positive particle fields of force in the same direction as electric field. The displacement is in the same direction. Work is force dotted with our displacement. So that's a positive work. Was there a traffic problem this morning? Breakfast issue?
There's a waking up problem.
Oh, waking up problem. Listen, when I was in high school, we had like an AP physics class, and it was sort of like this, about this size. And it was a boarding school. We would all meet in the cafeteria, and some days we just decide, hey, we're all gonna go in late. But we would do it like we'd all dress up, we'd all wear like ties and stuff. And then we would all go in, we'd like march into the classroom like 20 minutes late. Man, our teachers were pissed. We did it like 3 or 4 times, but they were very upset about it. Yeah, well, I mean, okay, you can do what you want. You can come to class or not. But this was high school, so it was a lot different. All right, so let's see. Has the potential energy of the positive charge increased or decreased here? If I have this positive charge that moves from left to right, does the potential energy increase or decrease? That is, what does delta PE do? If it's increased, it's positive. If it's decreased, it's negative. What does delta PE do? All right, just about 10 more seconds, yeah. Oh, A is increased, I'm sorry. B is decreased. Has it increased or decreased? Has the potential energy of the positive charge increased or decreased? All right, I'm going to stop at 55. Unless we have it right. All right, B is the right answer. And that comes up, you know, we had this PE is the negative of the work done. So as I move this charge from this point to this point, it gains some energy, right? What type of energy does it gain? It gains kinetic energy, taken from that reservoir of potential energy. And our conservation of energy still applies here, like we had last time. So anytime we have a decrease in one energy, like in the potential energy, we have an increase in another energy. All right. We've sort of been through this argument all along with gravity, but it still applies here. And so the result of this is the conservation of energy, that if I have a decrease of energy in one realm, in our potential energy, then it increases in the other, in kinetic energy. So if positive work has been done, the energy has gone into kinetic energy, right? The potential energy is decreased, the energy has gone into kinetic energy. So if the charge has lost potential energy at point B, its kinetic energy must have increased. If it has, it's sped up. Then we can calculate the charge's velocity at point B. And that's just that the change in kinetic energy is the negative of the change in potential energy, which is 1/2 mv squared. This is really a useful tool that if you have a particle of an unknown charge, or if you have a particle of a known charge, you can put it into an electric field and over a certain distance give it a very defined velocity. So it has a lot of applications for various tools that you might use, especially you chemists, where you need to determine unknown particles or accelerate particles to certain speeds. We'll see this in a couple of chapters when we look at mass spectrometers. So mass spectrometers use this idea along with the ideas of magnetic fields to determine the mass to charge ratio of unknown particles. So it's a very useful thing to understand that if I have these charges accelerated over a certain distance in an electric field, we have a very defined velocity for them. So let's just do the simple question. I have a proton released at -2 centimeters. In this electric field, what is its velocity at 8 centimeters? I'll give you just a minute to get started on that. Don't forget that you need to convert these distances to SI units. So I'm moving from -2 to 8 centimeters. So what is my total delta X there? 10 centimeters, right. Which is 0.1 meters, right. Right, so I want to know what is its velocity after it moves through this electric field of 1,000 newtons per coulomb at 8 centimeters. And here we're assuming that the electric field is in the same direction as the velocity. So I have a situation like this, electric field. I have a positive particle initially at rest, and it moves 10 centimeters across that electric field. I want to know its velocity at 8 centimeters. First I just find the work, and I'm setting that equal to the kinetic energy. Because whatever work that electric field does, the force times the displacement, will give me the, the kinetic energy. I'm going to give you the mass of our proton and electron. Mass and charge. You all should know these though. They're just good numbers to know. The mass and the charge of a proton. Alright, what'd y'all get? Y'all get a velocity? Yeah, negative 27 kilograms is the mass. Okay, yeah, that's right, 140,000 meters per second. Y'all agree with that? Okay. Yeah, so here I have everything I need, so I'm solving for V. That's going to be 2QE delta X over M, the square root of that. That's 1.6 times 10 to the minus 19. E was 1,000 per coulomb, and then 0.1, thank you, divided by our mass, which is at 1.6. Excuse me, 1.67 minus 27. And I get which marks at 140,000. Alright, you can see a simple question like that, maybe. There's some in the homework too, but it's an important idea that if I accelerate a particle over an electric field, I get a very defined velocity. And very accurately determine its velocity. Same with the gravitational field, right? We did that as well. Alright, can I go down from here? Okay, a couple more things and we'll do some more quicker questions. We're going to be talking about, like later we'll get into circuits and we'll talk about potential difference, and voltage. And those are all largely the same things, except potential difference is the difference in potential between 2 points. So we'll talk about the difference in potential between point A and point B. Right, there's a certain potential here, there's a certain energy per charge here, and then there's a certain energy per charge here. But the potential difference is very similar to potential, except for you're talking about the difference between 2 points. So this electric potential difference between 2 points is the energy per charge that is gained as the charge moves from point A to B. So delta V then is equal to the potential at point B minus the potential at point A. And so that's going to equal our change in potential energy over Q. Or actually, more particularly, we're just going to say that it's energy per charge. That it is our change in energy, or more generally rather, our change in energy per unit charge. And so this is a basic idea of what is potential. Remember, 3 big ideas. Forces, fields are forces per charge, and then potential is energy per charge. A potential is a measure of the amount of energy that a particular charge has. What is the amount of energy per charge? Our units for potential difference, and voltage are all in volts. And 1 volt is equal to 1 joule per coulomb. Because potential is a measure of what for what? Everybody all at once? Potential is a measure of what over what? All together. It's a what? Energy per charge, right? It's energy per charge. So that's a very basic idea, but it's an important idea that potential is a measure of energy per charge. So when you get 120 volts out of your electrical outlet, that tells you how much energy. If you have more voltage, if you have 240 volts, then you get more energy per charge. And we'll see later that that'll actually give you a higher current. Those charges have more energy, so they move more quickly, and they pass more energy along to one another. All right. Okay, so now I want to do a quick little derivation of sorts. We're going to come to this later, and I'm going to go and present it just a little bit here. So since our change in potential energy is QE delta X, and since our potential energy is delta PE over Q by definition, and this is equal to negative EX delta X, all right, these are just sort of things that we've written already, then we can say then that E in the X direction is equal to negative delta V over delta X. So our electric field is equal to, and we'll see this later, the negative of the change in the potential divided by the change in your X. Okay. Notice that we're talking here about the electric field in the X direction. So the electric field in the same direction as your change in direction, as your change in position, will equal this delta V over delta X. And anytime we see a delta over a delta, that reminds us of what? A change in something with respect to another variable. What does that remind you of? Okay, a slope, right? It's a slope. What else is it? It's not a ratio. Closer was the slope, but a fancier way of saying slope is what? Alpha 1. A derivative. Thank you. Yeah. So anytime I see a change in something over a change in something else, I can think of those deltas instead of deltas. I can think of them as e's, right? When we write a derivative. So I can say then that EX is equal to dV dx, and later we'll introduce the concept of a partial derivative. This is a thought cloud, so it's not terribly relevant right now. But later, we'll introduce this concept of a partial derivative, which is a lot like a derivative, where our electric field is equal to the partial derivative of d with respect to x. And we'll do that towards the end of the chapter. And we'll look at, if you have an expression for your potential, then it's really easy to find your electric field and to go back and forth or to find your electric field from it. We'll see that. It's really easy. You probably haven't seen partial derivatives, but they operate a lot like a regular derivative, so no fretting. This also gives us sort of a more typical unit. We talked about this just briefly, but before in the previous chapter, but a Newton per Coulomb is the same as a volt per meter from that. And that's sort of the typical way to express electric fields, Gary?
Line makes the
Oh, those are ones. 1 Newton per Coulomb equals 1 volt per meter. No, it's a 1.
Makes it a lot easier.
Maybe at LSU they give a different meaning to that line, do they? Okay. Yeah, so 1 Newton per Coulomb is 1 volt per meter. I'm sorry, I don't mean to pick on LSU. It's a fine school. And I mean, a lot of y'all want to go to LSU, right? Or will be going to LSU. Okay. What's that? It's just a 1.
No,
just you?
Just one person is one.
Is that you?
Yeah.
Okay, and Christian too. Yeah.
Okay.
Yeah, all of you engineers are not finishing here. I guess we have a lot of chem majors though, right? Like this whole group is chemistry, is that right? Yeah. And this group too. Well, no, yeah, you're still chemistry, right?
Yeah. This is pretty much the entire sophomore department. I don't know what I gotta do with my chemistry.
Oh, there's lots you can do with a chemistry degree, right? You can work, I mean, you can go to grad school, of course, and do research, and that's all very exciting. You could graduate and work in the chemical industry, or, I don't know, there's lots to do. Pharmacy, yeah, pharmacy.
I think I'm not going to do anything with chemistry.
You want to perform. It's quite the opposite here, you know. Very good, very impressive. All right. You have to tell a story. Actually, you mind? There's often when Americans see Chinese students, they think that Chinese students are very focused, and that's true that Chinese students are very focused, but they think that they're focused to the detriment of other areas. And I found that that's not really true of my Chinese students. That you're very broad in your interests. So I told her that that's not really true. All right. So anyway, particles tend to lose. Where was I? Yeah, energy. Oh, I don't know what this was. We're gonna skip this little part. I'm sorry, but we're gonna start here. Sorry, that wasn't in my notes. I don't know where that came from. So positive charges will accelerate from high to low potential. I'll show you where this comes about from in just a second. And negative charges accelerate from low to high potential. All right, always forget these two rules. And you can see a multiple choice question regarding this, but I always forget these two rules where I have which direction do these charges go. This is useful, by the way, because we can develop if we can create a potential field, which is very easy, and we can move around charges however we want. Or we can even isolate charges and make them not move at all. I'll show you, we can create like a potential well where the charges are isolated and they remain where they are without moving around. Because, you know, it's hard to move around charges. You can't take tweezers and move them around. You have to manipulate them in some way. So if I have a positive charge, I think about two plates. I have a positively charged plate and a negatively charged plate. Now the positive plate is a high voltage, a lot of energy per charge, and the low voltage plate is a low voltage. Excuse me, the negative plate is a low voltage. There's not much energy per charge. So if I put a positive particle here, it moves from the positive plate to the negative plate. So it moves from high to low potential. And then conversely, if I put in a negative particle, it's going to move away from that negatively charged plate, so the negative particle will move from low to high potential. You with me on that? Yeah, so if you ever forget, like I always forget, positive charges, what do? You just draw your little plates there and think about the direction that your positive charges move. Excuse me. And positive charges move from high to low potential. All right, so let's think about this. Oh, the answer's there. I'm sorry. So if I have a positive particle, you can put A. The answer's there. I'm going to take it off. There used to be a faculty member here several years ago, Dr. Baker. You remember Dr. Baker? Yeah. Oh, I love that guy. I know that the students didn't really like him that much because he was pretty tough, and sometimes he was a little crass. But he was such a nice guy. And he sort of livened up the department. Like, we go to meetings. I know that y'all think that we're really exciting, but at meetings and stuff, it's really boring. They're very boring meetings. Some of you will probably get to sit in on some. But Dr. Baker, man, he would liven things up. He would just sort of say things that were off the wall. But anyway, he had an exam once, and by accident, when he was making out of the exam, he put all the correct answers in bold, just like as he was making it out, so he could sort of think about what the answers were and what have you. But of course, when he printed it, he forgot to unbold the answer. So he handed out the test, and every correct answer was in bold. And nobody told him either, was the thing. Nobody told him. All right, he was not very happy. So positive particles released at a position of x equals a, where will the particle go? Well, positive particles move, remember, from high to low potential. So what I've done here is I've graphed v versus x So right here, it has a certain potential. It wants to move from high to low potential, so it's not going to move in this direction because the potential will be increasing. It's going to move in this direction while it will decrease. So it will move to the left. So to the left is the right answer, A. Let's stop this. 135. And if I have a negative particle, the answer here is D. It will oscillate around B, so we're going to put in D. If I have a negative particle wants to move from low to high potential. So it's going to move in this direction, but when it gets here, it's like it has extra energy, and so it overshoots where it really wants to be, and it comes over here, and then it oscillates back and forth. So you can set up the system in this electric potential that you've created with an electrical circuit that causes this negative particle to just oscillate back and forth. And it turns out that it oscillates at a very regular frequency, kind of like a pendulum. As it oscillates in the gravitational field, this charge will oscillate in the electric field. Alright? So it's a lot like a pendulum in that way. So the answer here was D. D is the right answer. I'm going to stop at 58. Okay, what if I put a positive particle right here? And I'll call this B right here. So what if I put a positive particle at that point? Which of these will it do? Will it move to the left, right? Will it be stationary? Or will it oscillate around B, that point B? If I put a positive particle there, I place it there at rest. What direction does it go? To the left, the right, stationary, or will it oscillate around that point? A positive particle. All right, I'm going to stop at 52. 52. All right, C is right. So positive particles, remember, want to move from, what is it? They want to move from high to low potential, from that positive side to the negative side. And already it can't move any lower potential, so it's just isolated there. It doesn't move at all. So this is important, sort of alluded to this earlier, but this is important because it allows you to move charges around however you want. You can keep them in a certain place, or you can make them oscillate around certain points. It just allows you to move charges around, which is actually not very easy to do. So this is important. You can hold charges. At a point, or cause them to oscillate back and forth. You were doing that of sorts when you did the little video game in the lab. Remember that? And you were generating an electric field. And I actually think in that you could turn on the electric field, and that by having that electric field caused you or allowed you to move those other charges around as you like. Yeah.
So in the original question where you had x equals a, like if you had put it right at the top, like right at the peak,
right,
it would just stay there. But if you put it off of the peak, it would oscillate back and forth.
All right. Well, which particle, if I put it here, would just stay here? A positive or a negative particle? A negative particle. Yeah. So a negative particle, which wants to move from low to high, it wants to move to a higher potential.
But it's already there.
It's just staying right. Yeah. But if you move it like here, it's going to move up here, and then it will oscillate back and forth. I think I'll talk about this in physics, if I'm not mistaken, when you get into quantum, in a little bit different connotation. But All right, y'all did these. I'm not going to do them here. If you're not in the lab, you could take a look at this, but it allows you to see the electric field configurations of different configurations of charges, and then also there's this cool little video game that I'm sure that you've all been playing, right? Like you got to remember your Xboxes and your PS3s and all that, and you've been playing electric field hockey, right? Am I right? All right, okay. Let's do a few questions, and I'll hand back your test. All right, so a proton and electron are in a constant electric field. You release the proton from the positive side, the electron from the negative side. Which feels the larger electric force? So they're in an electric field. It's the same for both. Which feels the same, the larger electric force? Oh, I'm sorry. Let me start this. We'll just go to about 8:15, and I'll hand back your exam. I'm going to stop at 40 seconds. 40. Let's see, most of you put E. They feel the same magnitude force, but opposite direction. That's correct. So they feel the same magnitude force. They have the same charge, right? Protons and electrons, and they're in the same electric field. So they're going to feel the same force, but in opposite directions. Okay, same question, same scenario. Which one has the larger acceleration, the proton or the electron? Are they at the same? There is no acceleration, the same magnitude, but opposite direction. Yeah.
For the answer A and B, also the LCS is the magnitude of the acceleration of
Actually, let's just get rid of the answer E. So let's say E is not an option. Does that make it simpler? Does that answer what was your question? Ask your question again. I'm sorry.
you mean the acceleration in that magnitude of the acceleration?
The magnitude of the acceleration, yeah. So which one has the larger magnitude of acceleration? Is it the proton, the electron? They have the same magnitude of acceleration, or they don't accelerate at all? All right, just a few more seconds. I'll stop at 125. 125. All right, B is right. The electron, they feel the same force. We've had a similar question to this. They feel the same force. Electron has a much smaller mass by a factor of like 10,000, and so it feels a much larger acceleration by a factor of 10,000.
We don't say the magnitude in the proton, it has a positive acceleration.
You're right, yeah. You're right.
Much larger.
Right. Mm-hmm. Okay, same scenario. Which, when it strikes the opposite plate, will have more kinetic energy? They're in an electric field between these two plates. Which has more kinetic energy? They're both released from the same point. Or rather, they both cover the same distance, rather. Which has more kinetic energy? They're sort of all over the board. Ask your neighbor what they put. See if it's the same as you. Why y'all looking at All right. Let's see, we're still sort of all over the board. I'm going to stop at 125. This goes back to our sort of our idea of what is potential. Remember, potential is energy per charge. Both of these charges are going across the same potential, right? I have a potential difference between here that's the same. They both have the same charge, so how are their energies going to compare? They're going to be the same. Because they're both going across the same potential, then they both acquire the same amount of energy. So C is the right answer. Just a couple more. Oh, actually, no, we won't do this right now. All right, I'm going to hand back your exam. Stop right there.